Welcome to MOVITRAC LTP-B Basic and Intermediate Training. This is Session 9. This session is what I call the Miscellaneous Topics session. We're going to cover a lot of odds and ends that aren't even related to each other. We're just kind of clearing out some concepts that I think you'll find useful. This session is sort of the gateway to the more advanced concepts that we'll be covering in our next several sessions. So, without further ado, let's get going. We're going to begin by talking about the hybrid outputs. This is sort of indirectly connected to terminal control. It's not specifically part of it, but we've been covering a lot of things similar to it, so this is a good topic to cover first. Let me just remind you, the MOVITRAC LTP-B has two hybrid outputs. These are outputs on the I/O connector that can function either as analog or digital outputs. Here they are right here. They're labeled A01, D01, and A02, D02. So these can be either digital outputs or analog outputs, obviously not both at the same time. Probably a good idea to remind you of their electrical specifications. When they're outputting in digital mode, they behave in the classic 24-volt digital logic used with many industrial control systems. In other words, when the output is high, it'll be outputting close to 24 volts, and when it's low, it'll be outputting something near ground potential. In analog mode, they can output a variety of voltage and current signals, but the maximum voltage they can output is between 0 and 10 volts DC. In either case, digital or analog, you should never draw more than 10 milliamps from an output. All right, so what can you do with the analog and digital outputs? Well, in digital mode, they can provide the same kind of feedback to an external controller as the relay contacts could. We've already looked at how you can use the relays. You can do pretty much the same thing with the digital outputs. For example, if you have a PLC that has 24-volt digital inputs, you can connect an output directly to it. Of course, you always need to remember to connect the ground connection on the PLC to the ground connection on the VFD so they're at the same potential. So you can use these outputs, much as you did with the relay, to tell the PLC what the VFD is doing. In analog mode, the signals can provide a voltage or current that represents a process value. This can be extremely useful because it can give the PLC or other external device some very specific information about what's going on with the VFD. The most common way of setting up the analog outputs is in voltage mode, where you get a voltage between 0 and 10 volts that represents the process value. For example, let's say we just hooked up an ordinary digital multimeter to our VFD. We connected the negative terminal to the ground connection on the VFD and the positive terminal to A01. We then configure the output in analog mode, and in this example here, it's showing a voltage of 6.75 volts. Now, what does that mean? Well, that depends on what process value that voltage represents. The VFD can represent 4 process values in this way. It can indicate the speed at which it's running, the amount of current the motor's drawing, the torque that the motor's delivering, or the power that the motor is using. Now, in most cases, you probably aren't going to hook a digital multimeter up to your VFD. You're more likely to connect a digital controller like a PLC that's equipped with analog inputs. If you wire the analog inputs to the VFD, the PLC can acquire the information, convert this into a process value, and use it to make decisions. Let me give you just a quick example here. Let's say we're configured in 0 to 10 volt mode. First of all, what that means is 0 to 10 volts represents a percentage between 0 and 100%. That means a voltage of 6.75 volts is equal to 67.5%. Now let's say we've configured our VFD to represent speed with an analog value and it outputs 6.75 volts. That's 67.5% of the maximum speed. Now you would need to know what your motor's maximum speed is. Let's say it's 1800 RPM, that's the value in parameter 1-01. It turns out that 67.5% of 1800 RPM is 1215 RPM. So what your PLC program would do is it would take that analog voltage, convert it to a percent, do some math, and it could then know how fast the VFD is running the motor. So very useful, something you can definitely take advantage of. So how do we configure the analog and digital outputs to do what we want? Well, it's relatively simple. Parameter 2-11 configures analog output 1, digital output 1, and parameter 2-13 configures analog output 2, digital output 2. Both these parameters are in the extended parameters group, and they configure the AODO signal's behavior. So we'll take a look at one of these. They're identical. This is the one that configures analog output 1, parameter 2-11. These are the choices that you can assign to it, and these will tell it what it needs to output. It will also indicate to it which mode to be in, digital or analog. Now, if you look at the first 8 of these, you might say, these seem very familiar. And the answer is yes, they are. They're exactly the same digital outputs that were available for the relays. So these are all status outputs. They're identical to the relays. They can tell you things like, is the drive enabled? Is the drive healthy or faulted? Is it at the target speed? Is it running at a speed greater than 0? Or is the motor speed, current, or torque crossing an upper or lower limit? So this is very familiar ground. You don't have to learn anything new to use these. Everything here works exactly as it did with the relays. In fact, the limit parameters are the same ones used with the relays. They are shared with the relays. So if you're going to use limits, you are going to have some limitations as to how many outputs can be set up in this way, since there are only 2 sets of limits, but there are 2 relay contacts and 2 analog digital outputs. We're not going to spend much time on these because this is the same as what you've already learned. Instead, we're going to focus on the analog parameters. And these are the ones right here. There are 4 of these. These represent speed, current, torque, or power as an analog value, typically of voltage. The last 2 are kind of interesting. These are used when you're controlling your VFD in field bus mode, and you can send a value over the field bus that will be expressed as an analog value from one of these signals, or you can send a digital, that is just an on or off signal, over the field bus, and it will operate one of these outputs in digital mode. We will not be looking at these in this class, but I did want you to know what they do. Now, if you configure one of your hybrid output signals in analog mode, in other words, it's going to represent a process value, you do have to configure its analog behavior. So you need to go to an additional parameter, 2-12 or 2-14, depending which signal you're configuring. And you need to assign it so that it will control the format that the analog signal will come out as. These are your choices. Your first 2 are voltages. Now they differ only in the direction that the voltage increases or decreases. The first one increases from 0 to 10 volts as the process value increases from 0% to 100%. The second one is sort of the inverse of that. The voltage drops from 10 volts to 0 volts as the process value increases from 0% to 100%. So they're pretty much the same idea, but simply operate in opposite directions. The last 4 choices output current values. Some industrial control systems use current to represent process values. We won't be working with that in this class, but do be aware of these if you do have current-based equipment that you wish to work with. So 0 to 10 volts is the default, and it's the one that's most commonly used because it's generally very useful for many applications. In fact, it's probably time to demonstrate this. So let's go ahead and demonstrate how to configure the analog digital outputs, and then we're going to also see how they behave in different scenarios. So let's go into LT Shell and set this up, and then we'll go ahead and demonstrate it. Well, we're in LT Shell here, and I've already scanned in and connected to my VFD. We're set up the way we were last time, so we need to go ahead and make a few changes in order to demonstrate using the analog digital output signals. I'm going to turn on real-time edit mode, and the first thing I'm going to do is confirm that I'm in terminal control mode, parameter 1-12, and yes, I am. But I don't like this variant in parameter 1-15. I'm going to change to variant 1, which is pretty much just our standard stop, run, forward, reverse, run with the potentiometer, run with the preset speeds. I'm going to be using the potentiometer to control my motor, so that will work. So that's everything I have to do here. Now I'm going to go to parameter group 2, and I'm going to configure the analog output. I'm going to use analog output 1, so this is A01, D01. So I go to parameter 2-11, and I need to select its function, what it's going to represent. I want to be sure it's in analog mode, so it'll be outputting a voltage, and I want it to show my speed by this voltage. And it just so happens its default value is speed, so actually I didn't need to change it. It's currently set to speed, but of course I could have picked current, torque, or power, but speed is fine, so we'll leave it in that. I also need to check its output format in parameter 2-12. And it is set right now to 0 to 10 volts. So the voltage was going to track the speed. Remember, 0 to 10 volts is equivalent to 0 to 100%. So that is all I have to do. I don't have to set up anything else. I should be all set. If I run my VFD and put it in potentiometer control mode and ramp that speed up and down, my voltage should kind of follow it. So let's go over to our VFD, hook a voltmeter up to it, and try that out. We'll turn off real-time edit mode first, and we're all set to go. All right, well, let's start our VFD by turning digital input 1 on, and I'm just going to pick a random speed, and you can see the voltmeter there. It's tracking what's going on. Now there we are. We'll just stop there at 627 RPM. You can see we have 3.5 volts, so let's do some math. This is 35%, so 35% times the top speed, which is 1800 RPM, is 630 RPM. So we're within 4 RPM of what the display is showing. So that's pretty good. So there's an example of an analog signal tracking the VFD's process value. Now let's just go ahead and turn our VFD off, disable it, and move on. All right, well, let's move on to a totally different topic. We're going to talk about faults. Now, we have been talking about faults on and off through the entire course because they're a regular part of life whenever you're working with industrial control equipment. But this is really the time I'd like to spend formally talking about faults, how we manage them, and especially how we learn enough about them to solve them. So let's talk about some of the things you do when things go wrong with your VFD. Of course, the place you always go first when you have problems is the keypad and front panel display. It's the first place to look for information. It will display a brief fault message on the display when a fault occurs. And of course, it's also the place you usually go to clear the fault. Remember, pressing the stop button on the VFD will clear the fault and enable the VFD to go back into operation, assuming whatever problem caused the fault has now been corrected. I'm going to just give you a warning that I've given you before, but I'm going to give you again. How the VFD behaves after you clear the fault depends on parameter 2-36. We'll be looking at that parameter in much more detail later in this session, but this parameter controls whether the VFD will restart immediately upon having the fault cleared or whether the VFD will clear the fault but not start operating. Remember, you should always be safe when you clear a fault by assuming that the VFD could restart immediately, and you should take appropriate precautions. Obviously, you don't want somebody getting hurt or something getting damaged when you clear a fault. But we'll be looking at how you can control the restart behavior later in this session. Let's talk about some of the most common faults that appear on VFDs. There are many, many more faults, and I refer you to the manual for the explanation of the more obscure ones, but I'd like to talk about the kind that you'll see fairly frequently. Of course, we've seen this one recently. This is the external sensor trip message, E-trip. It goes off when you have an external sensor connected to the VFD and the sensor's output has gone low. That will cause an external sensor trip message. Closely related to that is the motor temperature protection trip. This is actually simply a specialized version of the external sensor trip, and it just indicates that the motor has overheated and the VFD is shutting down to protect it. OT indicates that the heatsink has become too hot. The heatsink cools the IGBTs within the VFD, so this is the power electronics section of the VFD. If you see this message, it means the VFD's IGBTs have gotten too hot and it's shutting down to protect itself. If this happens, you probably want to take a look at air circulation to make sure that the VFD is getting adequate cooling, make sure that the heatsink isn't covered with dust or there's a problem with the fan, or it's simply not getting enough airflow. These three messages all relate to overcurrent or overload situations. There are subtle differences between them, and I refer you to the manual to understand those. But if any one of these comes up, it probably means your motor is pulling too much current. Now that could be for a number of reasons. It could mean the motor is stalled or jammed. It could mean there's some kind of an electrical problem. There are many possibilities. It could even mean you're using a motor that's the wrong size for the VFD. It's too big for the VFD. So if these come up, you need to look up the specific message in the manual and then see if you can figure out how to correct it. This message indicates that the brake resistor has been overloaded. Remember, the brake resistor absorbs regenerative energy when the VFD is slowing down the motor. If the brake resistor is taking on more than it can handle so that it could be overheating or become damaged, the VFD will fault and give this message. So if that happens, you want to look into why and also consider is your brake resistor sized properly. If you see this message O-volt, it means the DC link is receiving too high a voltage. What this means is that it's receiving regenerative energy and it's not able to handle it. If you don't have a braking resistor installed on your VFD and you receive this, it indicates that the motor is generating energy, pushing it back into the VFD, and the VFD cannot handle that. So you should probably have a brake resistor installed. If you do have a brake resistor and this happens, then you have other problems going on and you probably want to investigate more deeply. This last message is one you've probably seen fairly often because every time you turn off the VFD, you will see this undervoltage message on the display briefly before it shuts down. That, of course, is not a true fault. That happens simply whenever you power it down. But if this does happen during operation, it could mean your line voltage is dropped, or it could mean there's some other problem with the DC link in your VFD. So these are your very common fault messages, but as I say, there are plenty of others. This is just a sampling of ones you might see fairly often. Now, where can you get more information than just by looking at the front panel of the VFD? Well, the answer is you can get a lot more information if you go into LT Shell and connect up to the VFD, scan into it, and go to the Group 0 Parameter tab, the read-only parameters. There's a lot of information in here. You can learn a lot about what's going on in the VFD, and if it's faulting, you can use this group of parameters to try to track down why. Now, don't forget, if you want to monitor the VFD in real-time mode, you have to scan in, then enable real-time editing, then go to the Group 0 tab and check the refresh boxes of any parameter that you wish to live monitor. If you don't check the refresh box, you don't turn on real-time edit, you will see a static copy of those parameters. You won't see them live, so don't forget that. So here's some of the information you can find on the Group 0 page. The Group 0 page, as you know, contains read-only parameters. You can't change these, but if you set these up to refresh, they will change live to show you what's going on in the VFD. The trip log, parameter 0-13, is really handy. It shows the 4 most recent faults that have occurred on the VFD. You have a time indication as to when they occurred, and you also have a text description telling you what the fault is. It's more detailed than the front panel display. Very handy to look at. The DC bus voltage gives you an idea how healthy the power section is. Incidentally, the DC bus voltage or DC link voltage should be about 1.4 times the maximum output voltage of the VFD. So if you have a 230 volt VFD, the DC link voltage should be about 330 volts. If you have a 460 volt VFD, it should be about 650. You notice mine shows 653, so it looks healthy. And if you have a 575 volt VFD, it should be almost 805 volts. So the DC bus voltage is very important. It gives you a good indication of the health of the power electronics. The heatsink temperature tells you how hot the power electronics are getting. So again, gives you some good insight into the power side of the VFD. And then finally, the DC bus ripple voltage is useful too. This should always be a very small value, just a few volts. If you see it becoming rather large, it could mean there's a serious problem, either with the capacitors that filter the DC bus, or possibly you could be creating an overload situation and the filter capacitors are just getting overdrawn. So these are things to check to give you an idea about the VFD's overall health. Moving on. Parameters 0-28, 0-29, and 0-30 contain information about the VFD itself, such as its firmware version and information about the hardware. This is extremely helpful if you have to call SEW Eurodrive for technical support and speak to an engineer. You might be asked this information. Also notice your drive serial number is available right here. Now, several key parameters are stored in logs that show the last 8 values associated with a fault. These give you historic information on these parameters. For example, there's one right here. The last 8 values of the DC bus voltage at the time of a fault. So you can look at these to see what was going on when the VFD faulted. So this gives you history of the DC link. DC bus ripple is available. You can see its history as well. Notice all these are very low values, so there's nothing really wrong here. The heatsink has an 8-value history. Also, the internal temperature does. This is the temperature of the internal low-voltage electronics that control the VFD. This is separate from the heatsink temperature. This is what's going on inside the VFD. There's also a motor current log that tells you how much current the motor was drawing at the time of a fault. In each of these cases, nothing looks too bad. The motor was only drawing a very small amount of current. But if you see a large value here, that could definitely point to some kind of an overload situation. There are a number of counters that tell you how often critical faults occur. You might look at these. If you see a very high value on one of these, you should look into its reason. Take a look at parameter 0-43. That's the undervoltage fault counter. It's got a count of 67. Now you might be tempted to think, boy, there's something really wrong with this VFD. But remember, every time you turn off the VFD, you get an undervoltage fault. So that's why this number is so high. This number will typically be high, so it's not a terribly useful counter because it kind of gets masked by normal shutdown faults rather than actual faults. And then finally, there's one more here, parameter 0-72. This gives you the current internal temperature of the VFD's ordinary low voltage electronics. This is not the power section. This is the regular electronics. Okay, so this gives you an idea what's going on inside. So that's some information about faults and about understanding how your VFD is performing. Now, we have talked about how the VFD restarts itself after a fault in the past, and we've certainly observed how the VFD handles startup when you power it up. In fact, you may have seen some behavior as you've been playing with your VFD that mystified you. We're now going to take a detailed look at how the VFD handles startup and restart behavior. I think you'll find this interesting, and this will give you the ability to really control how your VFD behaves. As I've mentioned in the past, parameter 2-36 and the extended parameters determines how the VFD starts up and restarts. It's very crucial that you understand this parameter because if you set it wrong, you can get some very mystifying behavior. It can also be potentially dangerous if you don't understand it. So I'm going to try to clarify how this works. Parameter 2-36 is the start mode select parameter, and it defaults to what's called auto 0, but it has many additional choices. These are the choices that are available: edge R, auto 0, and then auto 1, 2, 3, 4, and 5. So what do each of these do? Well, let's start by looking at auto 0, which is the default. What this basically tells the VFD to do is to automatically start or restart as long as it has an enable signal. So let's take a simple example. Let's say you have a VFD and digital input 1 is the enable signal. You turn digital input 1 on and then you switch the VFD on. The VFD could potentially start up immediately as soon as it receives power. That is because it's in automatic start mode and it's enabled. It may not start automatically. It depends what other modes are configured, but it is at least possible. Now let's consider a second scenario. Let's say our VFD is in auto 0 mode. It's running and then a fault occurs, maybe an over temperature situation on the motor. So you allow the motor to cool down. You press the stop button on the VFD's front panel. What will happen? The VFD will simply restart immediately because the fault has been cleared. So auto 0 will allow the VFD to either start up automatically or restart automatically if a fault has been cleared. This is the reason I've been giving you warnings periodically about the VFD restarting when you clear faults, because auto 0 happens to be its default behavior. Now, you might be thinking, that's actually kind of dangerous. I don't want that to happen. I don't want the VFD to automatically start up, nor do I want it to automatically restart after clearing a fault. Can I do something different? And the answer is absolutely. That's what edge R is for. If you change to edge R, which is option 0, the VFD, in order to start or restart, requires a rising edge on the enable signal. So let's say digital input 1 is our enable signal and it's on. Your VFD is operating, doing its thing, then a fault occurs. If you press the stop button, it will clear the fault. However, the VFD will not restart until digital input 1 is turned off and then on. That generates a falling and then a rising edge. So that will prevent the VFD from restarting automatically. You have to restart it intentionally. The same is true for starting when it powers up. If digital input 1 is left in the on position and you power up the VFD, it will not start running automatically until you turn digital input 1 off and then back on. So edge R is definitely a little bit safer, but it is definitely more manual. So you do have to do more to make the VFD run. The reason we have all these options is just to give you flexibility, but you do need to use them intelligently. Now, what's the deal with auto 1, 2, 3, 4, and 5? These are automatic restart modes that attempt to automatically restart after a fault. The number indicates how many times it will try. So auto 1 will try once to automatically restart after a fault. 2 will do 2 times, 3, 3, 4, 4, and 5, 5. This can be used to have the VFD sort of auto-recover from intermittent faults. Let's say, for example, the VFD overheats, it shuts down, it cools off. Instead of requiring an operator to come and clear the fault, if you put it in one of these auto modes, the VFD will wait a certain amount of time. It defaults to 20 seconds, but you can set it to other times. And then it will attempt to restart. And if it successfully restarts, everything will just go back to normal. Now, if it faults again, it may or may not automatically restart. It depends what number you've selected of the 1 through 5 number of retries. Let's say you've set it to auto 2 and it's already automatically restarted itself twice and then it faults again. It will not reset it the third time automatically. You'll have to manually go in and restart it by pressing the stop button. This may be a little confusing, but I'm going to demonstrate it and I think you'll understand it much better as soon as I've done that. You should be aware that the auto start mode is potentially a little dangerous. So I'm just going to give you a warning here. When you're in an auto mode, always be careful since the VFD can restart automatically. Now, modes 1 through 5 automatically attempt to restart after a fault. They do it up to 1 to 5 times. The time interval that they try to restart it is set in parameter 6-03. It defaults to 20 seconds, but you can set it to shorter or longer values. But be aware of this, that if you have one of these enabled, the VFD could fault. It will then try to restart, and maybe it doesn't restart for 20 seconds or longer. Now you've walked away and suddenly, boom, the VFD restarts. That could definitely take somebody by surprise. It definitely could cause an injury. So if you operate in one of these auto modes, do be aware that you could get a restart maybe minutes later. And it will look unexpected, but actually it isn't. It's just the VFD doing what it's supposed to do. So understand these modes, use them intelligently. They can really be your friend. All right, well, I'd like to demonstrate this. So we're going to go into our VFD. We're going to play with several of these modes. I'm going to demonstrate auto 0, edge R, and then I'll show one of the auto modes where it attempts multiple times. We'll use auto 2. So let's go into LT shell and we'll get this set up. All right, well, we're going to experiment with several of these start, restart modes, and we're going to start with auto 0, which is the default. I'm going to enable real-time edit mode, get set up so we can play with this. First of all, we are already in terminal control mode. Parameter 1-12 is set correctly, but I do want to pick a different variant for parameter 1-15. I want to pick variant 6. And the reason is this one has the external fault sensor. We're going to use that to trip some faults so we can see how the VFD handles starting and restarting. So I'll pick variant 6 here. And finally, then we need to go to parameter group 2 and just confirm we're in the correct startup mode. So we'll go down here to parameter 2-36 and start mode select is set to auto 0, which is the default. That's the one we'll be using. So we're all set now. We'll go ahead and test this out. I'll turn off real-time edit mode and we'll go to our VFD. All right, let's test the auto 0 mode. I'm going to show you how it handles starts and restarts. First of all, notice digital input 5 is on so we don't trip a fault. Now I'm going to turn on digital input 1 and ramp up my speed. This is just normal behavior. We'll turn it off. Now what we're going to do is power off our VFD, and we're going to wait for it to power down, which will take a few seconds. And we've powered down. Now I'm going to turn digital input 1 on to enable the VFD and switch it on. And you notice it immediately starts running as soon as it gets power. Let's trip a fault now. I'll turn digital input 5 off. There we go. We have a temperature fault. I'll turn it back on. And I'll clear the fault by pressing stop. And you notice the VFD immediately restarts. So this is auto zero behavior. Okay, well, we've seen how auto zero works. Now we're going to go ahead and look at edge R. So I'm going to re-enable real-time edit mode. I'm going to go to parameter 2-36 and change it to edge R. Don't have to change anything else. We'll turn off real-time edit and we'll go back to our VFD and we'll play with this and see how it differs from auto zero. Okay, we're now configured in edge R mode, so we're going to try to start the VFD and we're going to try to restart it after a fault, so let me demonstrate both of those. All right, we're still in potentiometer control mode. You see we start up when we turn digital input 1 on, and I'm going to turn it off now. I'm going to power down my VFD and wait for it to shut down. That'll take a few seconds again. And as soon as that happens, I'm going to turn digital input 1 on to enable the VFD. There we go. Now I'm going to power it up. And you notice this time it doesn't run. It's in stop mode. I have to turn it off and then on to run my drive. Let's trip a fault. And let's clear the fault. And you notice again it doesn't restart immediately. I have to provide an edge by turning digital input 1 off and on. So that's edge R mode. More manual, a little bit safer maybe. We want to look at one of the modes where it will automatically attempt to restart. So we're going to again turn on real-time edit mode, and I'm going to pop parameter 2-36 down and pick auto 2. Auto 2 will make 2 attempts to restart, so this will be interesting. We also need to set the time interval it's going to use, so we have to go to group 6 for this. It's parameter 6-03. And it's right up here, auto reset time delay. By default, it's 20 seconds. That's kind of long for this demonstration. I don't want you to sit and wait for a very long 20 seconds every time I demonstrate this. So I'll change this to 5 seconds just to make it a little quicker. All right, let's disable real-time edit mode and go test this out. All right, we're going to look at auto 2 mode. This mode will attempt to restart a maximum of 2 times. So we're going to play with that and I'll show you how that works. All right, let's start our VFD running the motor. We'll turn it on and we're going to trip a fault. And I'm going to remove the fault by turning digital input 5 on. Now let's just wait. See, there it restarted within 5 seconds. I'm going to trip it again and get rid of it again. And there we go, it restarted again in 5 seconds. That's our second restart. Now I'm going to trip it a third time and get rid of it. And as we wait, we're going to notice something. Now it doesn't restart because we've exceeded our maximum number, which was 2. So I have to clear it manually by pressing stop. So that is auto 2 mode. All right, now we're going to take a look at a closely related topic, and that is how the VFD behaves when it's operating in keypad control mode. It has start and restart behaviors in this mode as well. They are very similar to the ones we've just looked at, but they do differ a bit, so we need to take a look at these so we can understand how our VFD is going to work and not be taken by surprise at its behavior. Parameter 2-37 in the extended parameters determines how the VFD starts or restarts when it's in keypad control mode. That means parameter 1-12 is set to either 1 or 2. We've played with keypad mode on a number of occasions. Parameter 2-37 determines how the VFD behaves when it's in this mode. So these are the choices that are available, and you see really 2 groups that appear to be identical. 0 through 3 and 4 through 7 seem to be almost the same thing, but the first ones to have nothing after them and the second have terminal run after them. So what's the difference? Well, it means that when you pick 0 through 3, the VFD is controlled primarily by the start and stop buttons on the keypad. When you're operating in modes 4 through 7, the VFD is controlled almost like it's in terminal control mode by the I/O connector. It's sort of a limited terminal control mode that also has some keypad functionality. So when you operate these, you're going to get slightly different behavior. I encourage you, spend some time playing with these to understand how they work. There are some subtle differences between them, but once you've played with them, really it'll all just drop into place. So let's talk about what each of these options does. If you pick option 0 or option 4, which is minimum speed, the VFD, when it starts up, will run at the speed stored in parameter 1-02. That's the minimum speed. In many cases, it's 0. So if you pick this, your VFD may not run at all. But if you have a minimum non-zero speed in there, it will run at that speed. If you have option 1 or option 5 selected, the VFD will start up and go right to the last speed that it ran at under keypad control. You've seen this a few times when I've done demonstrations. Maybe you've noticed when I started up the VFD by pressing start, it didn't begin at 0. It jumped up to an existing speed. Well, that was just the last keypad speed that I ran at. And you notice option 1 is the default value. So this is what you will often see. Option 3 or 7 uses preset speed number 8, whatever speed is stored in there. Now, options 2 and 6 are a little bit different. They're used when you're switching from one VFD control mode to another while the VFD is running. If you have these picked, then the VFD will simply keep running at the current speed. So those are a little different. I've kind of treated those almost separately. So that's how the keypad behaves. Moving on, this is definitely a niche topic. We're going to talk about the switched IP66 models of the MOVITRAC LTP-B. As you recall, we talked about this early on in the course. The switched models have built-in direction control switches, and they have a speed control potentiometer. Now, you may wonder, is it possible to disable these since they do take up digital input 1, digital input 2, and analog input 1, digital input 4? Is it possible to disable or disconnect them in some way? And the answer is absolutely. If you don't want to use them, if you want to have all your I/O available, there is a way to shut them down. You do it through the parameters. So you need to go to a parameter in group 0. Now, these are the choices that you can pick. There are 8 choices. They're called set 1 through 8, and they have the controls selectively activated or deactivated. By default, set 1 is the one in force. Notice all 3 controls are activated. The clockwise, counterclockwise switch, and the potentiometer, but it is possible to turn these off selectively, and set 8 has all of them turned off. Now, how do you go in and set this to control this? You have to do it from the front keypad. You can't do it in LT shell. You do have to have the extended parameters enabled, so parameter 1-14 needs to be set to 201 for this to become visible. Then what you do is navigate to parameter group 0. Press and hold the stop button until set 1 appears. Then you can pick any of the other sets you wish, 2, 3, 4, 5, 6, 7, or 8. So pick the one that gives you the configuration you want. If you want to totally deactivate your controls, pick set 8. And then finally press stop again to accept the value, and that's that. So pretty simple, something you'll only have to do with this one particular version of the MOVITRAC LTP-B. All right, well, this is our last topic. We're going to look at bidirectional speed control with the potentiometer. And you're probably wondering, what's this all about? Well, let's talk about why we would want to do this. It's actually there to help us solve a problem. So what is the problem? Well, let's say we're creating a custom terminal control variant. So we're doing a totally customized setup, and we've discovered we're running out of signals. We don't have enough digital and analog inputs to do what we want. What can we do about this? Well, we could, of course, put in an I/O expansion card, but maybe we don't have one handy, or we've already got a card installed in the expansion slot that does something else, like a field bus card. So what can we do? Well, the answer is you can sacrifice the directional control signal that controls the motor direction of rotation to get one extra signal, and then you can manage rotation in other ways. Let me show you an example. Let's say that this is the variant that we've custom created. Digital input 1 is a stop and clockwise run signal. Digital inputs 2 and 3 form a 2-bit binary number to select between 4 speed sources. Analog input 1 is connected to a speed control potentiometer, and digital input 5 goes to an external fault sensor. Now you notice we don't have a direction control signal because we ran out of inputs. We can run the drive clockwise and that's it. But what if we need to run it in both directions, clockwise and counterclockwise? Is there a solution to this? The answer is yes, there is. The sign on a preset speed controls its direction of rotation. So if the number is a positive number, in other words, there's nothing in front of it, it will rotate clockwise. But if you put a negative sign on the preset speed when you set up the parameter, it will rotate counterclockwise. So you can use signed presets to get direction rotation. You don't need an explicit direction control signal. So that is one thing you can do. But another thing, and this is what I really want to show you in this section here, you can set up the potentiometer to control speed and direction at the same time. And that's what we're going to do. We're going to see how to use the potentiometer in this way. So let's look at an example of how to do this. Normally, the potentiometer operates as a unidirectional control. In other words, it works like this. When you turn it fully counterclockwise, you're at the 0% speed. The motor will be brought to a stop. When you rotate it clockwise, the speed will increase. When you are in the middle of the range of rotation, you're at about 50% of the motor's maximum speed, and when you reach fully clockwise, you're at 100%. So this is the way the potentiometer behaves by default. But you can reconfigure the potentiometer through parameters to be bidirectional. Now, what does that look like? Well, it looks like this. When the potentiometer is in the middle of its rotation, the motor is stopped. When you rotate it clockwise through half the range of rotation, you get between 0 and 100% speed. And when you rotate it counterclockwise through half of its rotation, you get 0 to minus 100% of its speed. So for example, if you have an 1800 RPM motor and you're configured to use the full speed, when the potentiometer is in the middle, the motor should be stopped. When you turn it clockwise, you'll go between 0 and 1800 RPM. And when you turn it counterclockwise, you will be operating between 0 and negative 1800 RPM. This is bidirectional control. So I'm going to explain how to set this up so you can use the potentiometer in this way and get full speed control. You need to go to parameters 2-30, 2-31, and 2-32, all in the extended parameters. These configure the potentiometer's behavior. So what you do is you go to parameter 2-30, that is analog input 1 format, and you need to change it to -10 to +10. What you're doing is changing how it interprets the voltage coming in. You need to set analog input 1 scaling, which is in parameter 2-31 to 200%, so you double the range that the potentiometer operates over. And then you change analog input 1 offset in parameter 2-32 to 50%. What that effectively does is shift the 0 to the middle of the range of rotation. So by changing these three parameters, the potentiometer will now give you positive and negative speed control. I think it's time for a hands-on. You need to put this into practice. This is going to be a challenge for you to use your skills creating a custom terminal control mode, and you're going to also take advantage of what I've just shown you with the potentiometer. So here's what I'd like you to do. I'd like you, first of all, to set up a custom terminal control variant using the signals shown. So digital input 1 is a stop run clockwise signal. So when it is off, it should stop the VFD, and on, it should turn clockwise. Digital input 2 and 3 will be the 2-bit binary number to select 4 speed sources. Digital input 2 is the least significant bit. Digital input 3 is the most significant bit. Analog input 1 will be the speed control potentiometer, and digital input 5 is a fault sensor input. So that means you will need to turn on your fault sensor so that it doesn't automatically trip. It needs to be set to a 1 to be signaling normal. So set this up. Then you'll have to set up these 4 speed sources. If you put a pattern of 0, 0 in, I'd like you to use the potentiometer to control the speed. If you put a 1, 0, I'd like you to access preset speed 1, which should be clockwise at 150 RPM. If you put a 0, 1 in, you should get preset 2, which should be 500 RPM in the counterclockwise direction, so set the preset to a negative value. And if you put a 1, 1 on these inputs, you should get preset speed 3, which should be set to 750 RPM clockwise. So those are your speed sources. Configure the potentiometer for bidirectional control, as I've just shown you. and then test everything out. Confirm you can access all the sources, confirm that the potentiometer runs the motor in both directions, check the fault sensor, make sure it trips, and hopefully everything will work out. So go ahead, pause the video, and do the hands-on. All right, well, let's go ahead into LT Shell, and I'm going to demonstrate how to set this up, and then we'll test it out on my demo unit. Okay, well, we're right where we were last time, so we're just going to pick up and make a few changes to implement the requirements of this particular exercise. I'll start up real-time edit mode. Now, we need to create a custom terminal control variant, so we'll just confirm we're in terminal control mode, parameter 112, and yes, it's set to 0 terminal mode. We need to change parameter 1-15 to 0, which is the user-defined control mode, and then we go to parameter group 9 because everything else lives there. All right, we're going to let our input enable source be the safe torque off signal, so we'll leave that at the default. We're also going to turn terminal control override on permanently, so we set parameter 909 on. Then we'll go ahead and assign some of the other inputs. We're going to assign digital input 1 to the forward run input source, and we're going to assign digital input 5 to the external trip signal. All right, that takes care of most of our inputs. Now we need to set up our speed sources. Our first speed source is to be the potentiometer, and it already is by default, so we'll leave parameter 9-10 set to that. Parameter 911, however, we're going to set to preset speed 1. The next one goes to preset speed 2, and the last to preset speed 3. So we're using 4 of our 8 possible sources. We need to assign some digital inputs to activate these sources, so we'll change parameter 9-18, which is bit 0, to digital input 2, and we'll change 9-19, which is the second bit, to digital input 3. And that is all we have to do as far as assigning things to make our custom control mode work. However, we do need to go and change some of the presets, so we need to go to group 2. And our first preset is to be 150 RPM in the clockwise direction. We set it to 150 and it's positive, which is clockwise. Our second preset needs to be counterclockwise at 500 RPM, so that means we change it to -500. And our last needs to be 750 RPM clockwise, so again, we don't put a sign on it, and everything will be fine. So now our presets are set up correctly. The last thing we have to do is set up the potentiometer for bidirectional operation. We'll roll down to parameter 2-30, and we need to change analog input 1 format from 0 to 10 volts to -10 to +10. We need to change parameter 2-31 from 100% to 200%, and parameter 2-32 to 50%. All right, we have to do just one final thing. We need to roll down here and change from auto 2 mode back to auto 0, so everything will restart correctly after a fault. And that is it. So now we'll turn off real-time edit mode, go to our VFD, and test this out. All right, well, we have everything configured. Let's check it out and see how it works. We'll go ahead and work through all the possibilities. Okay, first of all, notice digital input 5, the potentiometer's turned all the way up. That'll prevent a fault from tripping. And now I'm going to turn my main potentiometer to the middle position so the drive shouldn't be running too fast when I enable it. We're almost in the center. Notice that digital inputs 2 and 3 are both off. That's selecting speed source 1, the potentiometer. So let's turn digital input 1 on. And there we go. You can see it's running a little bit clockwise because it's not quite in the center. I'll turn it all the way up. We should be able to go to our maximum speed of 1800 RPM, and we do. Now let's go the other way. We're going to move down and we're going to go counterclockwise when we come off the center position, and there we go. And there we go. We clearly can get the full negative direction too. Let's move it back now to the center. And let's turn digital input 1 off. Let's pick our first preset by turning digital input 2 on. That gives us 150 RPM clockwise. It does. We'll turn digital input 3 on. That should give us 500 RPM counterclockwise, and it does. So we'll turn that off. And then finally, we'll turn both digital inputs 2 and 3 on. That will give us 750 RPM clockwise, and it does. Let's trip a fault, make sure that works. We'll turn digital input 5 off, and it trips. Turn it back on, clear the fault. Everything's good. So I think we're in good shape. And that is the end of session 9. It was a long session, but we had a lot of odds and ends to cover. We're now ready to transition to the more advanced concepts in this class. In our next session, we're going to learn about the built-in diagnostic tool, the scope, which is in the VFD and which can be used for all kinds of useful and fascinating tasks. So, see you next time.